We're talking about the multigrid method. In the last video, we focused on the coarse grid correction sequence, which is a 5-step process going between two grids. Let me just summarize it again for you as the basis for our discussion in this video. So the first step is to relax on the fine grid. That's the cap omega H grid. And we relax on the original variable using LU is equal to F, the original difference equation for U. We then calculate the residual, restrict that down in step 2 to the coarse grid, capital omega 2H, and then we solve the error equation for the error E on that coarse grid. We then interpolate the error back up to the fine grid. We use that to correct the UH that we had from step 1. Then we relax again several times on that fine grid. That is the coarse grid correction step. The question I left hanging in the last video is, how do we solve that error equation in step 3? So that's addressed using what's known as a V-cycle. So the quote-unquote solution, and this is why I put it in quotes in step 3, is actually obtained by recursively going down, down, down further in the grids. So we start with the finest grid, cut it in half, cut it in half, cut it in half as many times as we can until we get down to the coarsest grid possible for the given problem that we're treating. So let's take an example where we have 4 grids, omega H, 2H, 4H, and 8H. At each time, we're doubling the grid size and having the number of points in each direction. So the V-cycle would look like this. The open circles represent relaxation, the down arrows represent restriction, and the up arrows represent interpolation, just like I just showed you in the coarse grid correction. So we start on the finest grid. We relax several times, do 1 times. We calculate the residual and restrict it down to the next coarser level. On that coarser grid level, we solve the L is equal to R equation, where the R is the residual that we just restricted down from the finer grid. We solve for the error E. We determine the residual for that and restrict down to the next coarser grid. Now we have an equation for the error of U. So we relax on the LE is equal to R equation on that grid level, determine the residual for that equation, restrict it down again till we get to the coarsest grid. That coarsest grid might even be 3 by 3. At best, it's 3 by 3, only 2 intervals and 3 grid points. And then we go back up. So we take the error on the coarsest grid and we interpolate that up to the next finer grid. We use that to correct the value of the error that we had at that level. We then interpolate up again, correct, relax, interpolate up, correct, and relax. And that's a V. That's essentially one iteration in the multigrid method. It's that full V. And then you continue the V's until it converges. Now, if you're listening closely to my description of the V-cycle, you notice that what we're operating on at each level in the grid is not the same thing. On the finest grid, we're actually relaxing on the original equation for U. On the next coarser grid, we are relaxing on the error from that finer grid. And then from the next coarser grid, we're relaxing on the error from that previous grid. So as we get coarser in the grids, it's the error of the error of the error of the original U that we're actually operating on. In terms of writing the code, we just have functions that do restriction, interpolation, and relaxation. I can put in any quantity, it'll relax it. Any quantity, it'll restrict it. Any quantity, it will interpolate it. And so whether it's the error of the error of the error of U, it doesn't matter. I just put it in and we go on our merry way. So you'll notice when I discuss these specific operations, I'll present them as if they're operating on U. But in fact, they might be operating on U or the error of the error. They could be operating on the residual. They could be operating on any one of these quantities. Now, if you think of those V-cycles, we start at the top. We start with an initial guess on the finest grid, and then we do our V-cycles. If we have a good initial guess, then that's fine. We put in the good initial guess, we do our V-cycles until we converge to a good solution. And sometimes we do have a good initial guess. For example, if I'm solving an unsteady problem in time, and at each time step I need to solve a Poisson equation or a Laplace equation for some quantity, then I do have an initial guess for the current time step I can use the solution from the previous time step, and it's not going to change much, so that's a good initial guess. If we do not have a good initial guess, then we use what's known as full multigrid V-cycles, or FMG. The components, the ingredients in this cake that I'm about to bake, are exactly the same as before: relaxation, restriction, and interpolation. However, they're going to be done in a different order on different quantities in order to ultimately produce a good initial guess. So instead of starting at the top on the finest grid, if we don't have a good initial guess, let's start at the bottom on the coarsest grid, because those calculations are done more quickly, more rapidly, and we can work our way up to a good initial guess on that finest grid. So here's how it goes. You can see the steps articulated up here, and then they're illustrated down here. So let me illustrate it in the figure below. So in step 1, we're going to relax on LU is equal to F, the original difference equation, on the coarsest grid. You'll notice it's U, not E. Then we take U and we interpolate it up in step 2 to the next finer grid, where we then relax again on LU is equal to F. Then we do a V-cycle between those two grids in step 3, and then step 4, we interpolate up one more grid level, do the relaxation on LU is equal to F, then we do a complete V-cycle between those 3 grid levels. That's step 5. We interpolate up, and we just keep doing that until we've gotten to the finest grid level here. Once we have a good initial guess, we can then do our V-cycles. The point is, by doing this operation first, we get a good initial guess, so presumably we'll be doing fewer V-cycles as we go. So now I'd like to delve a little bit deeper into some of the details in the multigrid method. If you're not interested in these details, I give you permission to just skip through the rest of the video. So let's talk about grids. Because of the way we're having the number of grid points in each direction as we go down coarser, 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 and therefore our delta x's are doubling, doubling, doubling as we go from the finest to the coarsest grids, we need to think about the type of grid that we can impose. So in general, this is a 2n plus 1. And that will give us this capability to have, and then get down to that very coarse grid at the very bottom. That's pretty restrictive, however. So that goes 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. You know, for those, that's fine. The jumps are not huge. But when I get to 4,000, whatever it is, that's doubling now to something over 8,000. So you can see that the jumps can get very big. That restricts our flexibility in defining a grid that's appropriate for a particular problem. So we can do a little bit better by generalizing the number of grid points in the x and y direction as follows. Rather than just having one parameter, which is the n, 2 to the power n, we will have 2. So m and n. So we have for nx, little mx times 2 to the nx minus 1, and then plus 1. If the little m was 2, then this would still be just a 2 to the n sub x plus 1, just like we have here. But I can choose different values of m. I could choose 3, I could choose 5. That will give me a little more flexibility in the choice of my grids. We do exactly the same thing in the y direction. So what we would like to do is have the n's as large as possible, because that determines the number of grid levels. And we would like to have the m's as small as possible, because that determines the coarsest of the grids. The coarsest grid will be mx plus 1 by my plus 1. We'd like that to have as few points as possible in order to maximize the number of grid levels and therefore get the most efficiency gains, the most acceleration of our underlying relaxation technique. Let's look at some examples. These first two are 2 to the n plus 1. So 65, well, that's 64 plus 1. 64 is 2 to the 7, right? So 65, the mx would be 2, and the nx would be 6. So I have 6 grid levels, and the smallest grid would have 3 points, 2 plus 1. 129, same idea. So that's 128 plus 1. 128 is 2 to the 8th power. So in that case, again, the mx is 2, and the nx is now 7. So we have 7 grid levels to work with. But now we have the flexibility to get some other grid sizes between these 2 to the n plus 1 sorts of options. So here's an nx is equal to 49. Well, how do we get 49? Well, if little mx is 3 and little nx is 5, we have 5 grid levels, and the coarsest grid will be 4 by 4. Well, that would give us 49 points according to this expression. 81. How do we get 81? Well, little mx is 5 and little nx is 5. So it's the same number of grid levels as 49, but the coarsest grid is now bigger. It's 6 by 6. So you can see there's this trade-off between the m's and the n's, but it gives you this additional flexibility defining grids that are the best for your particular problem. Now, the number of grid levels is actually the maximum of the nx and the ny, because again, you want as many grid levels to work between and take advantage of this multi-grid methodology in order to accelerate. So we'll have capital N grids, so G1 through Gn, where GL is the generic grid at some particular level. And then here's expressions that you would actually use in the code. I won't go over the details of these, but this is how you'd actually define the size of each grid at each grid level L as you move up and down through the grids. Let's take a two-dimensional example. So let's say nx is equal to 65 and ny is 49. So we saw back here for 65 we have m is 2 and n is 6, and for 49 we have m is 3 and n is 5. So for 65, 2 and 6, for 49, 3 and 5. But what I want to show you is how we go from grid to grid to grid as we go from the finest grid, which is 65 by 49, down to the coarsest grid. We have 6 and 5. The maximum of those is 6, so we have 6 grid levels. G1, 2, 3, 4, 5, 6, G6 being the finest, which is 65 by 49. Now just watch how we go from the finest to the next coarser to the next coarser to the next coarser. Let's do the x's first. So we start with 65, subtract off 1 is 64, divide by 2 is 32, plus 1 back, and that's 33. Subtract 1 off, that's 32, divide by 2 is 16, add the 1 back, that's 17. 16 divided by 2 is 8, add 1 back is 9. 8 divided by 2 is 4, plus 1 is 5. 4 divided by 2 is 2, plus 1 is 3. And that's the smallest we can get in x. Now for y, we start with 49. Subtract 1 off, that's 48. Divide by 2, that's 24. Add 1 back, that's 25. 24 divided by 2 is 12, plus 1 is 13. 12 divided by 2 is 6, plus 1 is 7. From 7, subtract 1 off, that's 6. Divide by 2, that's 3. Add 1 back, and that's 4. We can't get any smaller than 4. So the point is, the way that we get this additional grid level is by having this one, but not this one. So the coarsest grid is then going to be 3 by 4, and the finest grid is 65 by 49. So you can see how you can choose these differently, again, as dictated by the problem that you're looking at. The next detail is boundary conditions. Now you could imagine how the boundary condition situation could be extremely complicated here. We have LU is equal to F that we're solving on the finest grid. We know what the boundary conditions are for those. That's from the original differential equation. But then for the next coarser grid, our equation is for the error. LE is equal to R. What are the boundary conditions for the error? And then the next coarser grid is the error of U. Well, what's the boundary condition for that error? And the next error, and the next error. So this seems like it could get extremely complicated and messy. However, it turns out, I won't show you the details, they're here. What happens is, on all the coarser grids, other than the finest grid, you're solving for the error, so you need boundary conditions for the error, and they're always homogeneous. So if the original boundary condition is Dirichlet, U is equal to 5, that's the boundary condition used for the finest grid, but for all of the subsequent coarser grids, the boundary condition on that error and the error of the error and so forth, those are all the homogeneous forms of that same boundary condition. So E would be equal to 0. So what happens is if you start with Dirichlet boundary condition, U is equal to some number, the appropriate boundary condition on all but the finest grid is E is equal to 0. And again, it doesn't matter which E. Is it the error or the error of the error? Doesn't matter. It's the homogeneous version. If you have a Neumann boundary condition on the finest grid, then you have a Neumann boundary condition on every coarser grid, but it's the homogeneous form of it. Same thing for Robin boundary conditions. So this is great news because no matter how many grid levels we have the same boundary condition on every grid level except for the finest grid. And the other good news, it's of the same form as the original boundary condition. If it's Dirichlet, it stays Dirichlet, Neumann, Neumann, Robin, Robin. So the form of the boundary condition is the same. It's just the homogeneous version for E. Now I also think about it, this makes sense, right? If I had a Dirichlet boundary condition, U is equal to 5, if I could specify a Dirichlet boundary condition for the error, what would I want it to be? Well, of course, I want the error to be 0, and that's exactly what happens. I specify the error to be 0 on the boundary.